Hi, welcome to the summit and welcome to the presentation of SolidCAM for mold making. My name is Amod Onkar and I'm the product manager for 3-axis and 5-axis milling in SolidCAM. Let's get started. SolidCAM today offers a complete solution for mold making. If you look at the process flow, SolidCAM offers the entire set of tools to begin right from the CAD part and end all the way up to the CAM of the inserts and electrodes. So if we look at the process flow, this is how the process flow is there in a typical mold making industry. We start off with a CAD part, which could be a SolidWorks part, a part done in SolidWorks. It could be an IGS, it could be a step or a parasolid that's been given to the customer from a third-party source. From there, the first step is to extract the core and cavity of the part, including the sliders. Once the core and cavity and sliders are extracted, actually there are three processes that can start simultaneously in SolidCAM. One, we can start making the mold design, the complete 3D mold design of the part using the core cavity and sliders that were extracted. We can extract electrodes, and we can also begin CAM of the core cavity and sliders simultaneously. All these three processes can actually be done parallelly, and the major advantage here is that once there is a change in the main CAD part, the entire change flows down to all the areas that are affected in the entire process, which means if there's a change in the CAD part, the core and cavity will get automatically updated. The sliders will be automatically updated. The mold design will be automatically updated. The electrodes will be automatically updated, and the CAM will be automatically updated. So it gives you one single stop solution for a complete integrated CAD CAM for mold making. So what are the products that we can see today in the entire process that we just saw? For our CAD area, we use SolidWorks, which is capable of doing any kind of paths, modeling, solids, and surfaces. It's also capable of handling third-party products or third-party files like IGS, Parasolid, STEP, VDFS, Direct NX, Direct Pro-E, Creo, Direct Inventor, or Direct Solid Edge. For core and cavity, we have a product inside SolidWorks which is integrated, which is called R&B Splitworks. For mold design, we have R&B Moldworks. For electrodes, we have R&B Electrode Works. And for CAM, of course, we have SolidCAM. We are the leaders in the integrated CAM. Right. So we are here to offer a complete solution for mold making with total associativity between the CAD into the core cavity, into the mold design and the electrodes and CAM. So the entire process is tightly integrated with each other so that changes happening in the main part trickles down the entire process and updates the entire process without any user intervention needed. Let's look at our first product, R&B Splitworks. Splitworks is a revolutionary product using advanced technology to automate the process of core and cavity separation and creation for the plastic molding, blow molding, aluminum injection, that's the high pressure die casting dies, investment casting, wax molding for ceramic technologies, etc. It includes automatic or advanced technologies to update the inserts after any modifications or additions to the part, including if the original part was an IGS or a Parasolid file. So that's very, very important. Right, so we will look now at our first product, which is Splitworks. Okay, so we have this product here, Splitworks, and this is the part today that we are going to deal with, which we are going to do the entire process with, starting from this part. So my first step inside Splitworks would be to assign or provide for a shrinkage. Since we are using a plastic part, the general shrinkage depends on the various plastics that are used. We are going to use a shrinkage of 1.5%. So I'm going to use 1.015, and I'm going to pick the part and we'll scale it up. So I have the scaling feature here. So I'm going to say this is shrinkage 1.5%. Okay. Right. Once we have had the shrinkage, we'll move into Splitworks and immediately create a core and cavity separation by clicking the split part functionality. And you can see that it's already created the splits for me. Of course, there are some surfaces where it can't understand. For example, the blue colored is a core area. Now you can see a couple of surfaces that have appeared from the core area into the cavity area. And if we analyze why, if you look at the visual analysis, you can see that it has got a negative draft, and that is the reason why this surface came from cavity to core to cavity. So what we can simply do is we'll ignore this at the moment and we will fix the other area. For example, we have got some surfaces here which are belonging to the core but have appeared in the cavity. So we'll clear some selections and we will accept this. And we will go into Smart Selection, select the surfaces that need to be sent to the core, and we will then accept this. So these are the surfaces that need to go to the core. So I will move them to the core area or to the core side. Okay, that's done. Let's analyze why this particular area came back here for the core area, or the cavity area has got assigned to the core. So I'm going to do a draft analysis with this plane as my reference, and you can see that we have got a negative draft here, and that's the reason why we had the surfaces attached to the core side. Right, so what we are going to do is we will attach, or we will insert a draft function with this as a neutral plane and these two surfaces as our surfaces for which we need the draft. And okay, you can see that the moment it got draft, Splitworks automatically identified and sent these surfaces to the cavity side from the core. Now, there are two more surfaces here which are marked red because Splitworks doesn't understand where the surfaces are going to go. Obviously, we're going to need a slider here. So I'm going to go to Splitworks, and you can see in the tree we have got cavity, core, and then there is two surfaces here which resemble both directions because Splitworks is unable to understand it. And then we have two more groups which are currently empty. So I'm going to go to the first one, which is this one. I'm going to assign this to side core 1. Again, Smart Selection, select this one, and we will move it to side core 1. Similarly, I will pick this and I will move it to side core 2. Okay. So my basic splitting is already done. So if I go to Splitworks and if I show you the part, how it looks like, this is how it looks like. Of course, this particular surface doesn't have any exploding direction, so we can assign the explode direction as that one. Okay, and then we go to the other side. Second one, set explode direction to this one here. Okay, so we are done with our split. So again, now if you explode the part, you can see that the side cores are moving exactly in the direction. You can also have the source part visible. And this is how our split looks like. Right, so our splitting is done. Now all we need to do is to create the inserts from with this. For that we will need to create our parting lines. So for that, the very first function, let us first save the file. I will create what we call as the unified surfaces for cavity, unified surface for the core, unified surface for the side core 1, and unified surface for side core 2. Okay. Once this is done, I'm going to go to the next command and I'll say plug holes, because I would like to close all these internal parting lines. You can see that it has identified all the internal parting lines, and we will close it in just one click. So this is an automated function to plug all the holes. Right, so that's done. Our next function is just hide the closed parting lines. My next function is to create the parting surface, which is a combination. In this case, in this part, we are going to use a combination of SolidWorks functionality and Splitworks functionality. So I will go to surface and I'll use the radiate function. And on the radiate, I will use this plane as my plane for radiating the surface, and I will pick some edges, just 3 edges here. That's good enough. 75 is the length of the radiation, and that's done. Now, the key thing here when we're using the SolidWorks functionality is we need to add one more step of knitting the parting surface to the main surface body. So we will insert another function here. Go to surface, knit, this one and this one. Now we have done the knitting. For the remaining area, we're going to use the Splitworks automated functionality of Loft. So I will use the function called Loft. So we need to pick, and it picks the body automatically. I'll start my loft from this point here, and I'll end my loft at this point over here, or even maybe this one. And we will use the reference edge as this one, up to this vertex. All right, accept it. Okay, so you can see that the loft is created very nicely. Now the advantage of using the loft function is that I don't have to do the knit again. It is done automatically. So let's do the remaining area using the same loft functionality. So my start point, end point, reference edge, and up to the vertex. Okay, the remaining one also is pretty simple. Start, end, 75. Okay, that's done. So my parting surface is ready. We will go to the next step to create the solid insert. So I will click on solid insert. You can see that it's already picked up the body. Okay, so we select the body, and based on the appropriate margins, Splitworks creates the inserts automatically for us. We can see that if I look at the parameters, it is given me a size of 255 by 180. I'm going to make this as 250 by 175. Okay, thickness 65 is good enough. What about the core insert? Also 250, 175, 65. Looks good. Apply this. You can see that once we applied, Splitworks created an assembly of the entire inserts, and it's brought me into an assembly environment of SolidWorks, which is now going to be the area where I'm going to work with. So it has created, we can see the part, We can hide that, and we have the cavity insert and the core insert. Okay, so I'm going to remove the transparency of both the inserts. And of course, let's hide the core insert. Let's look at the cavity insert. So you can see that very nice cavity has been done. I'm going to edit this function or edit this part because I would like to extract the core inserts, the 3 core inserts here. So I will create a sketch. Okay. Okay, that's good. And we will make the core insert here. So I'm going to make 3 circles. Okay, put the dimension to this. This is diameter 10. And then we will use the SolidWorks functionality. Sorry. Let's pick this, this, and this, and we will say they are all equal. Okay. So I have my sketch. Again, I'll go into the Splitworks command and I'll create sub-inserts. Pick the sketch. You can see that automatically Splitworks has recognized that we are going to create a sub-insert here. So I'm going to say circular base for the first, 5 millimeter depth, 15 millimeter in diameter. Similarly, circular base, 5, 15, circular base, 5, 15. Finish this. You can see that the inserts are now being extracted one by one from the insert, from the main insert, and we have our insert now, the cavity insert, and you can see the sub-inserts also extracted. Not only they are extracted, but they are placed also in the main assembly. You can hide that. And this is our sub-insert. Okay, so I'm going to save this, the main assembly. Yes. Now, if I switch off my core insert and look at cavity insert, sorry, and if I look at my core insert is still not complete. You can see that I have the side cores still fused inside. So let's go back to the main part and extract my side core. So I'm going to save this and I'll open the main part here. I'll go to the side core 1 and I'll say, not update surface, sorry. I will plug holes. Okay, so that's the area that we need to plug. So accept it. And then I'll create a function called as create side core. Pick this direction. I'll say this is 75 millimeter. Done. Okay, that side core is out. I will save this. And now if I go to my assembly is automatically updated. The side core is removed from my insert. Perfect. Let's go to this side because we also have another slider here. Go to my handle housing. Go to the second one. Plug hole. Okay, now this is not right, so I'm going to clear, pick this one, and now I will create a side core with this one, 75 millimeter, accept. Okay, this also is done. Save this. Going to go to handle housing assembly, and you can see even this side, both the sides, the sliders are extracted. All right, so I'm going to save this file and we will move to the next step. The next function is R&B Electrode Works. Now that we have extracted our sliders and core and cavity, we will move ahead and extract the electrodes for, let's say, the core area. So Electrode Works automates all aspects of extraction, design management, documentation, and manufacturing of EDM electrodes. One of the most key features in Electrode Works is its ability to apply spark gaps directly on the model, thereby eliminating the need for creating what we do in the manufacturing for negative machining. You don't have to apply any negative uh, offsets when you're doing the machining down the line. So Electrode Works has this ability to apply spark gaps straight away. Fully integrated with SolidWorks environments, Electrode Works guides you through the entire electrode design and production process. Right, we are going to see again now the Electrode Works. Right, so we have our cavity here. I just changed the color of the cavity insert so that it's much more easier to visualize how my electrode looks like. And we are going to move here from our process of mold making into the electrode area. So here we are going to use the R&B Electrode Works to extract the electrode. So we have a function here to add electrode from Electrode Works. So I'll click on add electrode. So the first thing it's asking me to create is an assembly file. So I'm going to say core electrodes. This is the name of my assembly file into which all my electrodes are going to be stored. Save this. Okay, so we have our part here and we are in our electrode design environment. Just go into the settings and I'm going to apply a reference corner as a chamfer of 2 by 45 because when you do the manufacturing, you would like to identify those two reference edges from where you're going to take the dimension. And obviously, I'm also going to color my burnt surface in red color. So any area that is extracted as an electrode will automatically get colored as red so that the CAM programmer can identify which areas are to be milled and which areas are now not. They need not give too much attention to it because it's anyway going to be done by EDM. So it's very important. Okay, so I will now pick a 3R blank and I'll say okay. Now I'm going to use a function here called as seed face where I'm going to pick one of the faces because we are going to do the electrode in this area. So I'll just pick this face here. And you can see that Electrode Works already has identified the other surfaces in that region and we have an electrode already done. All I need now is to identify or check the parameters. So we have the parameters function where we can see exactly what each of these dimensions mean. So we have A here, which is 88. So I'm going to make that 90. B is 22. I will make that 25. Just making that. And thickness, well, I'll just increase it to 45. Maybe even less than 45. Say 35. Okay, that's perfect. The total height, I'll just make it as 95, just giving them proper dimensions. So I have my electrode out here and we will extract it. Okay, so you can see that my electrode has almost been done. We are going to see the assembly straightforward into this. Okay, so you have the electrode. But what you don't have is that the electrode is exactly taking the dimension of the groove. So we'll go into our Electrode Works tree and right click on the Electrode Works. First, I would like to add some clearance so that I can pull this face out of the groove. So I'll add clearance. This is my clearance plane, and the surfaces that I need to add the clearance are these three surfaces. Okay, and the clearance parameter, I would like to go just 0.5 and tangent. Strand. Okay, so you can see that it's already pulled out by that amount. I will put the same clearance on the other side, these three faces. Clearance parameter 0.5, accept. Okay, next one, the most important one, is a spark gap. So I would like to add the spark gap to all my burnt faces, and I'll give a spark gap of 0.15 and accept it. So what you're seeing here now is that it has added the clearance, the spark gap clearance. So now it's given me a clearance so that my CAM programmer did not apply any of the negative offsets when machining. Once we have extracted the electrode, creating drawings is a breeze. We'll right click on that and say create electrode drawings. And I'm going to use a A3 sheet format, and I will have a separate drawing for manufacturing and a separate drawing for EDM. And I don't want to use the holder. Okay, and I'll accept this. Okay, so my electrode drawings are also done. So if I look at the manufacturing drawing, this is how my manufacturing drawing looks like. Everything in this is customizable, so nothing to worry. We get the dimensions of the electrode. Remember, I changed it to 90. I also changed the thickness. So all these values are automatically coming in from the assembly. And then I have the EDM drawing, which tells me on the EDM machine, how much do I have to move in X, Y, and Z to get to the position. So even that drawing is done in just a few seconds. You can see what I had told before, that whatever areas the electrodes are extracted, those areas are marked in red so that the CAM programmer can understand which area he doesn't have to focus much on, because he knows that this area is anyway going to be done by EDM, so he did not completely machine it. He can leave the material and go ahead and focus on the other areas. Moving ahead, we move into the mold design environment, and RMB Moldworks offers a premier 3D solid-based mold design application that delivers innovative, intuitive, intelligent design tools for the injection molding industry. So you can actually take the core and cavity and the slider that you have done and create the entire mold design inside SolidWorks using the intelligent, intuitive driven mold design tools offered by Moldworks. With more than 15 commercial component libraries like Hasco, DME, National, Progressive, PCS, Futaba, etc., Moldworks offers more libraries than any other product today in the market. So you name the component library or the catalog for mold design, those catalogs will be offered by Moldworks. Let's go ahead and look at a bit of Moldworks. So we are in our mold design environment, and you can see that we have already built up the mold for the part that we just did. So if I go into my plates and if I hide my static side, you can see that I have the two inserts, the core inserts, and the areas for our sliders. So I can show the parts. You can look, we also have the slider and the slider assembly out here. And if you look, we can apply or create all kinds of standard components like the screws and other things. So the entire design can be completely done in Moldworks. This includes also a very intelligent cooling design. So you can define a cooling cycle, and once the cooling cycle is defined, Moldworks will automatically apply all the components needed for the cooling design, including the pipe nipples, O-rings, etc., and the entire part. And you can also do the uh, the collision analysis to see if the pipe has come very close to any feature by giving a certain dimension. So all these functions are possible inside Moldworks. You can design the entire ejection mechanism, including the ejector pins and sleeves, and of course runners, gates, and whatever standard components that are there that can be directly created in Moldworks. This not only allows the user a great visualization tool but also can prevent a lot of errors that can creep in when you're actually manufacturing the mold. So once you have the mold, you can easily create the drawings needed for the mold. For example, I can go and create a drawing from this assembly, and we can use an A0 sheet. Right, and we can then just take and drop the views. We can have all the views here, and once you have the views, then you can obviously perform all the functions. For example, you can have all the hidden lines in all the views, or in this particular view, for example, you don't want to see the hidden lines. So I will say don't show any hidden lines. Here also don't show any hidden lines. Only in these two views I would like to have the hidden lines. Okay, so we can also apply, okay, we can also apply what we call as the ballooning. We call as the auto ballooning, and you can see that it balloons automatically. We can pick a certain view and the ballooning happens automatically. Apart from this, since it's a SolidWorks functionality, we can also create a table or bill of materials. Okay, so we can pick and we can apply. So you can have the bill of materials straight away done here. So all these functionalities straight away available inside Moldworks. So it uses the intelligence of Moldworks coupled with the powerful features of SolidWorks to create the entire mold design completely associated with the part that we have already done. I'm going to save this. Yes, save all. Okay, let's give that name as mold. Right, let's close and let's move ahead. Okay, we're going to move to the next step, which is a very important step of creating CAM programs for one of these inserts. I've picked up the cavity insert in this case, and we are going to do the CAM programming for the cavity insert. So let me go to SolidCAM, and we're going to start a new milling project. Okay, it's an external one, so I'll accept this. Okay, so I'm going to pick a 5-axis machine in this case. It's going to be a DMG 65 monoblock. Okay, and my coordinate system is the top center of the model box. So I'm going to put the coordinate system exactly at the center here. And my next step would be to define the stock. My stock in this case is actually going to be a wire cut block of this shape. Yeah, that's the stock. And my target obviously will also include the 3 planar faces that were used to plug the area where the core pins were extracted. So it's going to include also that. Okay, so I'm in my CAM environment now, and I can start preparing the or start creating the programs for my part. Now, I'm going to use a very powerful technique inside SolidCAM called as process templates, where I have already machined another part, a similar looking cavity, which is not the same shape, maybe close to the size, what we are seeing here, but definitely not the same shape. So I'm going to use a completely new mechanism of process templates, and we are going to apply the process templates here. Okay, let's go to the process. We'll apply it straight away from here. So I will add operations from a process template, and I've got the cavity machining template here. So you can see that I've got all the process set here. So I'm going to use the same name and click OK. Geometry is my target, and I'll click OK. Right, so you can see that my template has been applied. All I now simply need to do is to simply sit here and start calculating the toolpaths. No need to select the geometries again because I've used the function called the same name as target. So that's my first roughing toolpath. Let's calculate. So we're doing the rest roughing now. So it's calculating the stock. Okay. Start calculating the rest roughing toolpath. We are using a 12 corner bull radius 2 bullnose tool for our rest roughing. The previous tool, the roughing tool, was 20 radius 3. Okay, so what I'm going to do now is I'm going to just edit the operations and just look at the geometry, and we'll create the boundary because we need the boundary here. I'm going to save this. I will not calculate this toolpath. Okay. We will just edit this toolpath. Machining surfaces basically need to be identified. Okay, this is the machining surfaces, and we are going to do it anyway automatically. Okay, we'll just no. Pick this, yep. Okay, we'll save this operation. The red ones basically indicate that certain geometry is missing, so it's only the boundary that is missing. Save this, yes. Let's edit this. Boundary, I'm going to pick, yeah, that's it. That's the boundary, save it. Rest machining also. Use the same boundary. Yes. Save. Exit. So what I'm going to do now is I'm going to take all of these operations and put it for calculations while we can run our presentation again. Okay, so for CAM, SolidCAM offers variety of functions to machine any kind of mold, any size of mold in the way the user wants. For roughing, we have got three types of roughing. We have the generic high-speed roughing, which offers roughing as contour roughing, hatch roughing, rib roughing, and rest roughing. And then we have the new generation high-speed roughing, which was introduced a couple of years back, which has got hatch, contour, and rest. And then we have the patented product of eye machining, which can dramatically alter your machining times. It can save up to 70% and more of your machining time when you're machining the inserts on the CNC machine by using solid carbide end mills and going with a very high depth of cut and extremely high feed rates without compromising the quality of the cutting. You can achieve at least 70% of reduction in your cycle time. For finishing, again, SolidCAM offers a variety of finishing options. In the generic high-speed finishing, we have got the entire bouquet of offerings for finishing, like constant Z machining, hybrid constant Z, helical, horizontal, combination of constant Z with linear or constant step over, offset cutting, morph cutting, rest machining, contour rest machining, parallel pencil machining, 3D corner offset with a 3D constant step over machining, spiral machining. And then we have the new generation high speed finishing options, which are very fast in calculation. And here we offer constant Z rest machining, linear machining, constant step over rest finishing, and pencil machining. So we offer every kind of finishing coupled with the high speed surfacing function, which is capable of doing local area surface machining. You can machine any kind of part the way you want with an exceptional surface quality. So we have iMachining 3D, which is a proven solution for extremely fast and rapid machining of inserts for mold making. So they save up to 70% of time in machining time. It uses the proven iMachining 2D technology and then creates the Z step to create the scallops for you when doing the machining. Deep roughing, it uses the entire cutting length available on the tool, thereby shortening the cycle time and increasing the tool life. The entire parameters for machining, that includes RPMs, feed rate, axial depth of cut, radial depth of cut, everything is calculated by iMachining by giving just the machine to be used, the material to be cut, the ultimate tensile strength of the material needs to be given to iMachining, the tool to be used, and the geometry to be cut. Once these four items are given, iMachining will create an intelligent machining for the entire part without any user intervention. And you combine this with the HSM and HSR functionalities available in SolidCAM, it provides a complete machining solution for any kind of 3D parts. SolidCAM's HSR and HSM generic high-speed machining. They provide powerful roughing and the finest finishing tool parts for 3D high-speed machining of complex 3D parts, molds, and dies. It has got very unique machining and linking strategies for generating high-speed tool parts. There are absolutely no sharp corners. Everything is smoothened out. So they are suitable for the new generation high-speed machines that are there today. The cutting moves and retracts are smoothened to keep continuous motion. Retracts are kept to minimum to minimize air cutting. And all this translate into efficient, smooth tool parts that ultimately result in exceptional surface quality. The new generation HSR utilizes, it's a 64-bit calculation. It has multi-core support. The speed of calculation increases as your cores increase. So if you have got, let's say, 8 cores or 12 cores, with a 12 core machine, your speed dramatically increases over an 8 core machine. The recalculation is extremely fast because we store our parameters inside and only those parameters are changed and recalculated again. It also offers multiple surface offsets. You can create infinite number of groups. For example, in the figure that you see, the pink colored surfaces all have 0.2 millimeter stock, whereas everywhere else we are keeping 1 millimeter stock. So you can create infinite groups like this, very useful for dies, especially where they have to leave a different material on the parting surface. Different patterns are available. For example, hatch machining, uh, the contour style or the pocketing style. We also have a very powerful rest roughing functionality based either on the updated stock or previous tool. The user can specify a minimum stock thickness above which the toolpath will be generated. Arc fitting is available, which provides smooth transition between passes. The new generation SolidCAM Turbo 3D HSM, it's a new generation high-speed machining functions. Extremely fast toolpath calculations. You have to see it to believe it. Lightning fast recalculation of the toolpath. Assume that you have done a toolpath with, let's say, 0.5 step over and you would like to change the step over from 0.5 to 0.4. The recalculation is almost half the time of what it took for calculation. It's a true 64-bit architecture utilizing all the cores for calculation, minimum definition of parameters, and we have got all the functionalities available for machining like constant Z, linear machining, constant step over, rest machining. Toolpaths are available. Full gout checking, including checking with the holder, is also available. And then we have the HSS, which is the high-speed surface machining. It's an excellent complementary module for machining, high-speed machining of localized surfaces, advanced gout check for holders, arbors, and tool with the part. And it supports standard as well as shape tools. It can handle undercut machining, and it's a very important module for every shop, including the mold makers. So you can actually go and machine certain areas of the part without the need of defining any boundaries or anything. Just pick the surface and the toolpaths are created. Some of the examples of the machining, for example, this particular part was done on a Makino PS105, took 240 minutes. And this finish is as coming out from the machine itself. The same thing was attempted, the same part was attempted on an Indian machine, Jyoti VMC 850. Part was done in approximately 300 minutes, and this again is a finish coming out from the machine as it is. On the same machine, another part was cut using, this is again a mold steel part, 200 minutes. It's a pre-hardened mold steel, and the finish again is as coming out from the CNC machine. And then finally, this particular part where we did machine on AMS MCV 450. It's an Indian machine. Machining, this was again done on a pre-hardened mold steel, and the time taken was approximately 400 minutes. Right, you can see that all my calculations are already done, and let's have a look at each of them. For example, this was my rough, this is my rest roughing, this is my flat area finishing, where it's exactly machining those surfaces that are parallel to the XY plane. We have the semi-finishing and geodesic machining, which follows only this area here. That's simple one entry and one exit, spiral machining. And again, there's a rest rough. So we can apply rest rough even after we have done certain finishing. And then we have the constant Z machining and the linear machining here. And then finally the rest area machining. So all this is being done using SolidCAM. And what we see here is that the entire process was done just in a single window. We did not change any environments. We did not change the software. We kept the software the same. It was inside SolidWorks, single window integration. Now, another best part with the entire process before we end is the ability to generate G-codes and the ability to simulate the G-codes in the G-code simulator. So I'm going to pick the first one here and I'll generate the G-code. SolidCAM provides a Simcoe editor, which comes along with the software. We have given a tight integration between SolidCAM and Simcoe, so that once the G code gets generated, it automatically gets opened up in Simcoe. Okay, it'll load up Simcoe, and you can see that the G code gets opened up in Simcoe. And what we can do is simply go into the backplot setup. I've set the machine already. Go into the backplot window, and what you see is not only just the tool path, but also the stock and the tool. So I'm going to switch off my workpiece and also switch off my tool path, and we can run immediately the simulation. You can see that we can do a material simulation inside Simcoe, just not the tool path, but we can also see 3D material simulation in Simcoe using the entire G code, so that you can be 100% sure that your G code that has been generated from SolidCAM is absolutely perfect before taking it to the machine. The tool was not defined, the stock was not defined, nothing. I just exported the G code out, and we have the G code inside Simcoe, along with the stock, along with the part, and along with the tool holder, etc. Everything is exported. Okay, let's stop this. So the conclusion is that you can do any kind of part. You can take any kind of part, whether it is a SolidWorks part, an IGS part, step part, or a Parasolid part, generate the core and cavity design, extract electrodes, make the entire 3D mold design, and then generate all the CAM programs in one single environment of SolidWorks and SolidCAM. So it's very important that the entire process that we just saw can be handled from within SolidWorks and SolidCAM. Well, thank you very much for watching. Have a nice day.